we're going to continue the time series analysis. And I'm sharing already with you my iPad. So last time we were talking about the definition, different types of time series. We talked about stationarity, non-stationary time series, and how it creates a problem, which is the spurious regression. And we ended last Tuesday class by talking about how to check the time series we have, right? So we need to know whether I have a time series that is stationary or non-stationary, because I need to know how to avoid the spurious regression problem. All right, so we talked about the autocorrelation test, the partial autocorrelation test, the Pierce box test, which is known as the Q statistic.
Professor?
Yes.
Can I ask a quick question pertaining to the final exam, only because this is our last class?
Yeah, can we keep all questions about the final towards the end?
All right, sorry, thank you.
No problem. And we ended by the formal test, which is the Dickey-Fuller test for stationarity, and it's known for unit root test. Okay, so what we're going to do today is we're going to start from here, which is the Dickey-Fuller test again. And I already showed you the expanded version of the test. So let me show you from here. So we were talking about the Dickey-Fuller test, just a very simple model in which I have just one lag, which is one period in the past, just one period. Okay, so here we have YT minus 1, and all our concern in this test is just the coefficient attached to YT minus 1. Okay, so we need to know like whether this is equal to 1, which means we have unit root, or whether it's less than 1, so we have a stationary process. Okay, so it's a one-sided test. So we're talking about here. So we're saying it's whether it's equal to 1 or less than 1. Of course, we hope to get it stationary, because this way we can depend on the series to do estimations or to do reliable estimations. We can also depend on the stationary process in order to forecast what's going to happen in the next quarter, what's going to happen towards the end of 2020 in the GDP or inflation or whatever macroeconomic variable we are interested in. The expanded version of the Dickey-Fuller test, or the augmented Dickey-Fuller test, which is simply adding more lags. This is just up to lag P, but still our concern is the same, which is the coefficient attached to YT minus 1. And I want you to notice the way that this model is structured. Here I have first difference, or the change, and here I have the change everywhere except the coefficient I'm testing, which is the YT minus 1. And again, our concern is to test this delta and see whether it's equal to 0 or it's less than 0. And if it's less than 0, then this is the good news, because this means my series is stationary. I have also discussed the different versions of the Dickey-Fuller test. It all depends on how your model looks like, whether you have a model that has a constant, whether you have a model that has no constant but has a trend, which is connected with time. So we have basically 3 different versions of the critical values of the DF table. And I'm going to show it to you in the Stata application towards the end of today's class. So let's continue from here. So what if we rejected the null, or sorry, failed to reject the null? What if I have a unit root process? So if I rejected the null, if I reject the DF, the Dickey-Fuller, or let's make it more general, the augmented Dickey-Fuller, which is the big model. If I reject the augmented Dickey-Fuller null hypothesis, then the conclusion, as we said, or let me say, if I fail to reject, let me have the unit root. So if we fail to reject, then we have unit root process, right? Or in other words, the series or the variable is non-stationary, which is not good, okay? And if I have a series that is non-stationary, like it depends on time, it's moving with the time, really you cannot use it. You cannot depend on it to get reliable results, right? And if I have two of these unit root process, if I have GDP is equal to alpha naught plus alpha 1 inflation, and then I have, this is estimated, right? And suppose this one has unit root, suppose that this one too has a unit root, in other words, non-stationary, then again, we go back to our main econometric problem of this topic, which is spurious regression. What is a spurious regression? I get very high R square, but however, meaningless results. Why is it meaningless results? Because each one is actually connected with time. So I have kind of a third variable that is omitted from this regression and is exerting an important effect, right? So if I can imagine that I have this regression GDP T is, and everywhere I have T here because it's a time series process. Suppose I have delta naught plus delta 1. It is connected with time, okay? Plus probably I have some error term, which is VT. And then I have also the same for inflation T, which is, anything, which is delta 0 plus delta 1 T plus NT, which is the error term of this regression. So each one is connected with time. However, time is not included in this regression, okay? So if this happens, then alpha hat 0, alpha hat 1 would be inaccurate. So I cannot depend on them. I cannot depend on, let's call this one star. I cannot depend on the star model to do estimation, to forecast the future, because it's actually missing a very important factor, which is the dependence on time. So the connection between both might be related to time and nothing else. So if I have a unit root process, I need to do something, right? So you need to transform the series or the variable and make it, or to make it stationary. Okay, so you need to transform it to make it stationary, right? So I need to make it stationary, and if it is stationary, then I can take it as a good series that I can depend on it to do my estimation and probably forecasting if I'm interested. So how can we transform the variable? So if we take the first difference of the variable, right? So for example, change in GDP. So instead of working with GDP, I will try to work with the first difference in GDP. So if I have GDP, let's say this is time, this is GDP, and you will be able to try this after we're done with today's lecture. So suppose that you have this series like this. If you graph the first difference in GDP the first difference in GDP, you would probably get it like this. So you get it more stationary, less connected with time, all right? So one way of correcting that, let me just make sure that it's clear. So this is GDP, the first difference in GDP T, right? So one way of working with the series is try to get its first difference. You have two options. If I get a first difference, and of course you have to redo the ADF if this is a big model, or the DF if it is just a simple model test. You need to perform the test again. After you're done with the test, you have two options. I can be done, right? If I'm done, I'm sorry. If I'm done and I'm getting it stationary, right? Then you're done. If it is non-stationary, then again, you're going to go and get the second difference. Get the second difference. And if you, after you get the second difference, again, perform the DF or the ADF test, and you keep going, right? And one of the, so if it is stationary, we have certain terminology. If it is stationary, we actually, like, if it took me only, this is very important, if it took me only one time to difference the series to get it stationary, we call it integrated, oh my God. So integrated of order 1, and in time series we call it I1 as abbreviation. So when you see a series that is I1, you understand, okay, it took me only one time to difference this, or first difference, to make it stationary. However, if I take the second difference and I perform the test and I find it to be stationary, then it took me 2 times difference the series to get it stationary, as you might expect, integrated of order 2, right? And if it is non-stationary, and this is not usually the case, we usually stop by the second difference in most of our econometric applications. We don't go like to the third difference and so on. So if it is non-stationary, then you keep going to the same scenario, but just we're not going into this direction because most of our series will stop by I2, and that's it. One important thing to mention is, suppose I have a variable, or let me kind of summarize what I was saying. So if I have a series that is YT, okay, and from the beginning I downloaded this series and I find it actually non-problematic, so it's stationary, so it's perfect, right? Stationary. Then I actually call it I0. I don't need to do any differences to get it stationary. It's originally stationary. So this is called I0. If it is non-stationary, okay, then I take first difference. If it becomes stationary after I perform the test, then I call it I1. If it is non-stationary, okay, then I'm going to take second difference. If I take the second difference and I perform the test and I find it stationary, then I call it I2. If it is non-stationary, then again, I'm going to take, right? I'm just going to stop by I3 and that's it. Okay, if it is non-stationary, then take third third difference, do the test. If it ends to be stationary, then it's I3. If it is non-stationary, keep going. Okay, so keep going. But again, in most of the applications that we do, we actually, most of our applications, we stop by I2 and that's it. Okay, so if you try to think about inflation, if you try to think about unemployment, stock prices, most of these are just I2. So in time series analysis, the very first thing that we need to do before we start any estimation is to graph our the different variables that we have. And after we're done with graphing, this is what we see with our eyes. We need also to back up this with a statistical test. So we perform the Adf test. You can also perform the autocorrelation, the Pierce-Box test, all of these. But the most famous one is the Dickey-Fuller and the Augmented Dickey-Fuller test. You get your results about stationarity. Then after you're done, you need the series to be GDP needs to be stationary, and let's say inflation needs to be stationary, then done. You can use it now to start your estimations and predictions about future values. Okay, so let's talk about an example. Or before I talk about the example, let me just talk about the main outlines of today's lecture. So whatever we were talking about now was just a continuation of the DF test that we were talking about last time. So today we will be talking about important things. So we'll be talking about the AR model, autoregressive model. Okay, I'm going to be talking about an example. We'll talk about the mean squared forecast error. Okay, and this is a very important point, choosing the number of lags. Okay, so this is basically the main important points that we will talk about today. And let me just add here, we have two tests here. So, or let's keep the two tests on for now, because I'm not sure whether I'm going to be talking about them if I have the time. But I can show you a simple way, which is the sequential. You know this already, so it shouldn't be challenging. So we have covered something very similar. Okay, so what is the autoregressive? So autoregressive model is a very important model that is used in forecasting. So it's actually a model that uses the past values of the variable to predict the future. So if I'm like showing you this model here. So yt is equal to beta naught plus beta 1, yt minus 1 plus ut. This is called an autoregressive model of order 1 because I'm using just one lag of yt to predict yt. If I have a model that is up to yt minus 2, then it's an AR2. A very general way of writing the AR model is like this. Yt is equal to beta naught plus beta 1, yt minus 1 plus beta p, yt minus p, right, plus ut. And this is called an ARP model, where P here stands for how many lags I'm using of yt to predict yt. So the autoregressive model is the model that uses the past values of the dependent variable in order to forecast future values. So I'm sure that you can think of this model in a different way. So I can write it like, if I can say today depends on the past, I can make today tomorrow. So I can write it like yt plus 1 is equal to beta naught plus beta 1 yt today plus ut. So you're moving the model forward. And again, it's an AR1 model, but I'm just moving it forward. So if today is the second quarter of 2020, and I want to predict the third quarter, then I'm going to be using a model like this, because I want to forecast, right? So as you might expect with any model, if I'm saying that, again, I'm gonna write it again, if I'm saying that I'm using AR model to predict the future, right, using just one lag, so I'm just gonna make it simple model using just one lag, okay, or one past value of yt, okay, this is an AR1 model. Whatever you get out of this model is called yt plus 1 hat, like what we have done before, which is simply equal to the beta hat naught plus beta hat 1 yt. Okay, so this is similar to what we have been doing before. Okay, and again, this is just an AR1, but you can always expand it to up to 4 lags or whatever the number of lags that you wish. So again, we can compute the error, which is the difference between tomorrow's value minus the value of tomorrow that I did predict, okay, or forecast. And this error term, again, we can square it, we can take its average, and so on. So the error squared is just like this squared, the sum of the error from t equal 1 to capital T, then I can do exactly what we have done before, right? So it's the sum from t equal 1 to capital T. So the sum of the squared residuals, again, SSR. The sum of the squared errors, if you wish to call it sum of the squared errors, sum of the squared residuals, it's the same. But now our difference is related to tomorrow or the forecast. So that's why we call it forecast error. So just a note, like a name, forecast error, because it's related to the tomorrow's values. So we also call it the sum of forecasted errors, okay? And to give you an example, so let me show you this simple, it's not a simple, like we have so many numbers that we're gonna write. So let me show you this. Suppose that I have, this is a very important example. So it's about predicting inflation. So suppose that inflation is non-stationary. And I'm just making an assumption, okay? Suppose that we took inflation serious and it was non-stationary. Let me use the terminologies that we have learned. So let's call it unit root. So I have the inflation series and I find that it has unit root. I transformed it, I took first difference and I realized it's now stationary. So the conclusion is inflation is I1. I need to difference it once in order to get it stationary. Now, I'm going to use the model in first difference because this is how the series becomes stationary. So my model is like this. I'm trying to predict inflation. Let's assume that we have, that we're trying to forecast 2000, let me just, okay, let's write it generally now. So t plus 1 okay, is equal to beta naught plus the change in inflation, right, in T plus, oh, this is, how come you didn't ask me where is the beta here? So this is plus, this is beta 1, okay, and then this is beta 2, the change in inflation, T minus 1 plus beta 3 change in inflation, T minus 2 plus beta 4 change in inflation, T minus 3, plus you have UT, okay, plus UT. So this is the general form of the model that you are trying to estimate, taking inflation in first difference. Now, suppose I have this data set. So I have a data set on inflation, and you're given the data set for 2019, quarter 1, 2019, quarter 2, 2019, quarter 3, again, the last one, 19, quarter 4, and you're given values of inflation. Okay, so this is given to you in the question, let's assume, and then 3.8%, 4.4%, 1.6, right, and 3.5, and you're also given the first quarter of 2020, right, and 1, and it's equal to 2.4%. Okay, and you're also given 2020, assuming that we have it, okay, quarter 2, which we're currently in quarter 2, 3.1%. Now, the model is not in level, right? As you can see, the model is in first difference. So we need the first difference here. We need the data for the first difference. So you just get the difference between these two, and you find it as 0.6, and assume that this number is given to you. So everything that I'm writing now is given to you. So you're not computing anything. And then difference between these two is negative 2.8, 1.9, negative 1.1, 0.7, okay? So this is information given to you. You want to use the model hat to predict this value here, the first quarter of 2020, the second quarter of 2020. In other words, you're taking this data set up to here to predict the first future value, okay? So in order to do that, you are actually going to use the data that you have to plug it in here, in here, in here, right? And you will be estimating the model. So the first one, which is the in 2020, I'm gonna write it 21, is equal to, so you have estimated the model and you got that the intercept is equal to 0.02 minus, so this is 0.02 minus 0.26, and you need to write down here YT, okay? So I'm here, so this is T plus 1. The very first lag is this one, so it's going to be 1.9 minus 0.32, so this is the beta 2. You're going to take the T minus 1, which is negative 2.8, plus 0.16, which is the beta 3. I need now YT minus 2, which is right here, 0.6 minus 0.03, which is beta 4, times 2.9, which is the last one. After you do so, you get approximately a number which is 0.4. So this 0.4 is your first predicted value that you are going to, you're going to write it here. So I'm just going to clean this. So this is your first predicted value. So you're going to write the first predicted value here. So this is your first answer, 0.4. Okay. Oh, I'm sorry. Okay, 0.4. And now you're going to repeat the same to get this value. Okay, so now I want to get the 2020, the second quarter. So in order to do that, we're going to just, to replace these values with the okay. So 0.02, and now I'm here, and I need my first value here, and I'm going to be using this value, this value, this value. So I'm going to stop at the 0.6. So in order to do that, the 0.26 is now multiplied times negative 1.1, 1.9, right? And then the 0.16 is times negative 2.8, and the very last one is 0.6. All right, and then we get the number approximately equal. When you try it, you're going to be approximately negative 1.34. So you will go here and then you write your answer for the prediction of the level of inflation, sorry, the first difference of inflation second quarter 2020 is negative 1.34. Okay, so you have used the actual values of column 1 and 2, right? Column 2 is made of column 1, right? So this one is column 2 is made of column 1. I have used column 2 to estimate my model. I got the coefficients, which are the betas, and then I used the data, all this data, to do my predictions of 2 points in the future. Now, we're not done yet because we need to know what is the amount of error in my estimation. In order to do that, we first need to get our inflation. Like this is the predicted change, but now what is the predicted level? I know that the predicted level is equal to the original level I know plus or minus the predicted change. Okay, so I already have this value, which is inflation. It's the actual data set, but I have done my regression and I got a number here, which are the 0.4 and the negative 1.34. So I can use these green values, 0.4 and negative 1.34, to get the estimated level of inflation. So in order to do that, we are going to use the, okay, so we're going to be using the first one, which is going to be here, 3.5, which is the level, is estimated to increase by 0.4. So 3.5 plus 0.4 would give us 3.9%. Okay. Now, the next one is I have a value of 2.4. However, this value is predicted to fall by negative 1.34. So 2.4 is predicted to fall. So this one is negative 1.34. And the number that we got is 1.06%. So this is what we got for the level of inflation. Okay. Next, I need to compute the forecast error. So, and I'm sure that you will find this is relatively easy. So the forecast error is the difference between the actual value, the predicted value of first quarter of 2020. Again, the actual value of the second quarter minus the predicted value. So to get the forecast error, I'm going to write it as FE, forecasted error, of 2020 first quarter is equal to 2.4 minus 3.9, which is negative 1.5%. Okay, so I have a gap of 1.5 because my prediction was higher than the actual value by 1.5%. The second one, which is the forecasted error of 2020 second quarter, is 3.1 minus 1.06. We have a lower prediction, right, of the value, and this one is equal to 2.04%. So the actual value was higher than my prediction by 2.04%. The next is, what about the squared forecasted error? You know that we always square it because I really don't care whether I have it below or above. You might actually be interested to know whether your prediction is above or below, but by the end, we actually compare models based on the magnitude of deviation. So whether this is by taking the square or taking the absolute value of the deviation. So here I'm taking the square as we always do. So it's going to be like this number squared. So negative 1.5 squared, 2.25, 2.04 squared is 4.16, right? And the mean, and this is a new, it's not a new terminology, you know this already. What is the mean squared forecasted error? So the mean average, right, of the squared of the forecasted error, as the name suggests, it's the mean, right? So I'm going to take the average of these 2 points. So 2.25 plus 4.16, and you're just dividing it by how many points I'm forecasting. So I'm forecasting, after you get the number, you divide, no, let me write it in a better way. So plus 4.16, right? And then you divide by 2 and you get this number equal to 3.2. And then now the question is what I can make out of this number. So out of this number is just 3.2. The 3.2 is used for model comparison. So if I'm comparing two models, and of course I'm going to be looking for a model that has the lowest, right, mean squared forecasted error. But for now, I just have one model that has a certain number, so I'm going to keep it. Maybe I'm going to compare it with another model that has, let's say here we have a model that has I, right? So this model is AR3. So I might be comparing it with another model that is AR2, and to compare between these two models. So now we got this one as 3.2 for the mean squared forecasted error. What about the number I get here? Let's say if I get here, just I'm saying an assumption, okay? Suppose I got a number here, which is 4.5, then I'm gonna say, okay, the mean squared forecasted error here is lower. It's better using AR3. Okay, but now I'm just showing you one model, one number. What you can do with this number, nothing. You can just keep it in case you want to compare with another model. However, what you can do is you can actually compare these two values. So if you have a question about which quarter was better predicted, okay, so of course the better prediction means a lower amount of error, and you can look at the numbers here and you choose the lowest squared forecasted error. So based on the 2.25, 4.16, of course the first quarter of 2020 was better predicted than the second quarter. All right, so what else we can do? So I talked about let me check the outline. So in our outline, we talked about the AR model, the example I just talked about, the mean squared forecasted error. So let's talk about choosing the number of lags. As I was saying now, like I was just mentioning right now, and saying that I might be comparing models between, let's say, AR3 and AR2. The question is, which one is better? Which one is I should use? So choosing the number of lags, the number of lags, or you can think of it as the number of P. How many P's I have? Like P minus 1, P minus 2. Okay, so I have a model, let's say YT is equal to beta naught plus beta 1 YT minus 1 plus beta 2 YT minus 2 plus beta 3 YT minus 3 plus beta 4 YT minus 4. I'm going to stop here. And plus UT. So you have GDP series and you have an inflation series, and you're not sure exactly, or let's talk about GDP. So I have GDP and I'm not sure how many lags I need to use. So one way to determine the number of lags is to use sequential hypothesis test. And as I always recommend, you use the big to small approach. What is the big to small approach? You start with a big model and you keep minimizing it. So here, as you can see, I started with AR4. Okay, so there is no rule here, but people usually start with an AR4 in quarterly data set. So AR4 model, and you keep on minimizing it depending on the statistical significance of the very last coefficient. So you check the coefficient of beta 4. And if beta 4 and only beta 4 is statistically significant, then you stop and you conclude your model is AR4 and I'm going to keep using AR4. However, if, and I'm sure that you know the sequence after that. So beta 4 is insignificant, you're going to estimate AR3 model. Okay, so you're going to reduce your model, move from big to a smaller model, and you're going to check the very last coefficient, beta 3. Okay, so you will go here and you will be reducing your model from an AR4, and you're going to remove this part, and your model is going to stop here. And you will be testing the statistical significance of the very last one. Again, the same sequence, significant, then your model is AR3 and you stop, and that's it. And insignificant, then make it smaller and you keep going. So you keep going. So I'm going to write etc. Just keep going. So you keep looking at the very last coefficient and you keep minimizing it from big to small until you reach the correct number of P. Okay, I'm not sure why I said P's, it's just one P. So I'm just gonna make sure that the number of P, so YT minus 1, YT minus 2, YT minus 3, YT minus P. So P here is the number of lags. Okay, so the last thing I'm going to, not sure whether I have the time to talk about it. Okay, so let me talk about an expanded version of the model. So there are so many things to talk about, but just I'm going to select what I need to cover in the short time. There is also a different version, or like an updated version of this AR model that we call ADL-PQ. So the previous one was called like ARP. So this one is called Autoregressive Distributed Lag model. Okay, and this is called ADL. And the ADL allows us to add lags of another variable to predict our variable. So we already talked about Y. We use P, lags of Y, but I can also have X and its lags. So it's called ADL-PQ. So these are the lags of the dependent variable. These are the lags of the independent variable. So you can think of this one of YT, and these are the lags of XT. So the model would be like this. YT is equal to beta naught plus beta 1. YT minus 1 plus, okay, plus, let's have alpha 1 XT minus 1 plus alpha Q XT minus Q plus UT. So now you're using P lags of Y, Q lags of X to predict YT, and this is called ADL-PQ. We have also, you can expand this model, okay, by adding additional predictors. I can also have more than like different variables, right? So I can have additional regressors. Let's say I have Y, X, and Z, let's say. So you can have a model that is, instead of me writing here again, I want you to imagine it's like the same here, but I just want to save time. So I'm going to add here another variable. So I can also add, let's say, okay, let's have it lambda 1 VT minus 1 plus lambda S VT minus S plus UT. So I can have an additional regressors, right? So now I used to have X, but now I have also V, and both are used to predict Y, okay? And that's why we call it ADL-PQS. All right. Now, there are so many ways to determine the number of lags of X, number of lags of V, the number of lags of Y. I don't have time to mention all that. I have already said that I can determine this by using sequential. So you can use sequential hypothesis for the Y part. What about the X? There are many ways for the X, but I'm going to choose something that you know, so that it's not like too much. So to determine, if I have, let's focus on the ADL-PQ. So for the ADL-PQ, so select the number of P using sequential hypothesis test. Okay, now for Q, use block test. What is a block test? The F-Test. Okay, and again, you start from big to small. So I'm gonna start with ADL44 perform sequential hypothesis test on the lags of Y and a block test on the 4 lags of X. If this one is, if the very last one is statistically significant, if the 4 are statistically significant, then you stop and say, okay, ADL44 is my model. Okay, and if not, then you basically, you already know about the sequential hypothesis test. For the 4, you might drop the 4 and have it like a 3 and then test block of 3 lags. So let me, tomorrow recitation, like we have all about time series, but let me show you quickly here, let's say maybe in 10 minutes, and then I'm going to take Samantha's question about the final, and then I'm just going to talk about the final in general. So let me share with you my do file, and okay. So I have a do file here where I'm talking about macro data set, okay? And then let's take the data set. So this is, okay. So we have 9 variables, 193 observations. As you will learn tomorrow in the recitation, you have to tell Stata that you have quarterly data. So this is a quarterly data set that starts from 1957. First quarter all the way to 2005. So you have to tell Stata that it's a quarterly data set by writing this notation, okay? And you can actually skip this part or you can have it, but this is just telling Stata, take all my data set until the end. So it's just, if you don't write it, then Stata will perform the same. So you declare your data set, you describe and summarize and so on. Let's focus on, so we have 3 variables that we will talk about. GDP in Japan in thousands of dollars, CPI in USA, unemployment rate in USA. So we have 3 variables, okay? The very first thing is we're going to generate growth out of this real GDP. So this is a real GDP in thousands of dollars. What if I want to generate the economic growth in Japan, okay, variable? So it's the change in the log of GDP. So you create the log, you get the first difference by typing D dot. Okay, so D dot would generate the first difference of the log of GDP, and that way you create the growth variable. The same thing, this is just an index, this is the CPI. You take the log of the CPI, you take the first difference, this would give you the growth in the CPI, which we call inflation, okay? And this one is there is nothing, I didn't do anything here, I just renamed because I didn't like this name, so I just call it unemployment. But the author or the source of the data, they call unemployment LEHUR, I just decided to call it unemployment. So there is nothing like major here, okay? Now, let's see the graphs. Looking at the graph would give us some idea about whether...
Just a question, are you posting this online or is this going to be recitation for this week?
Yes, it's in tomorrow's recitation.
All right, thank you.
Mm-hmm. And looking at the graph, just one of them, it doesn't seem to be stationary, right? We need a variable to be kind of deviating up and down the 0 or up and down a certain constant to call it stationary. This one seems to be kind of slightly negative, right? But again, this is our eyes. We need to complement this with a formal test. For inflation, okay, it looks like an inverted V shape. It's going up, going down. There is some kind of a break in the data set, and our course will not cover a break in the data set, but I might have a variable that is actually stationary, but something happened in the first quarter of 1981 that makes it non-stationary. So if I kind of cancel this peak, I might be able to get it stationary. We're not sure. But again, this is what we see in the graph. For unemployment, again, It doesn't seem to be stationary, but we will be testing it. So performing the unit root test or the DF test is you just type the command dfuller, whatever the variable you want, you choose the number of lags that you wish. And again, I always like, in quarterly data set, I start with 4 lags. You can start with more lags as you wish. But usually in a quarterly data set, we start with 4 lags, and it all depends on how many observations, of course, you have. So let me show you the Dickey-Fuller test for growth. As you can see here, like the good news is the output gave us also the critical values under different significance levels. So you can also, like if you Google search Dickey-Fuller table, critical values, you will get it. But the good thing is Stata would give us the critical value, so we don't have to go to the table and check. I need to compare this value with any of the critical values you wish. And of course, this one is smaller than them all. So you are in the acceptance region. So in other words, I fail to reject the null of unit root. Okay. And again, anytime you're trying to analyze a statistic, just remember what is my null hypothesis. Here, this is in the acceptance region. It's much smaller than all critical values. So accepting the null or failing to rejecting the null of unit root. The conclusion is economic growth in Japan has a unit root. It's non-stationary. Let's do it for inflation, right? So you take it one variable at a time. Same here. So 2.522 is less than this one, so unit root. Less than this one, it's unit root. Less than this one, again, unit root. So under all conventional levels, you have a non-stationary inflation series. And you can also check it for unemployment. So what about unemployment? 2.3 less than all. So again, I have unit root. So the conclusion is, based on the DF test, I have, right, unit root in the 3. So the 3 are non-stationary. Now, as I said, we need to take a first difference and check if taking the first difference would make the variables stationary. To take the first difference, I can use the command d dot. And you can call it whatever you like. I always call the first difference d. So just to make my life easy. DGR is the first difference of growth, first difference of inflation. So we're just generating new variables, right? And these variables are in first difference and performing the test again. Okay, but I'm performing the test now on the variables in first difference. But remember, because I got the first difference, I have to make sure that the number of lags are reduced by 1. Because I have already, here I have used 4, then reduce it by 1 because you have already taken difference. So you're losing 1 observation. So reduce your DF test by 1 based on the first difference. So here what we get is, we got good news, right? So it's way above all critical values. Same for change in inflation, same for the first difference of unemployment. So under all, like for all the variables, we are rejecting the null of unit root, and we're concluding that they are all stationary, which is good. I can depend on them now. And if I difference a variable once, as I said, and I get it stationary, I call them just a name, I1, integrated of order 1. What I have here for you is how you can do it manually. Like, as you can see here, you just type dfuller and in the background, Stata is doing the work for you. But you can actually do it by hand and you will get the same result. As you can see here, I'm saying towards the end, you cannot see it, but it's not part of your final exam. So do not expect me to ask you to generate the DF test by hand or manually, but I have it here for you for your own learning, is to show you how to actually create the DF test by hand and see that it's just showing you the same results. Okay, what else? Okay, I didn't have the time to show you the information criteria. Okay, so let's talk about it in terms of sequential hypothesis test. And I'm going to make sure that tomorrow's recitation is not covering the information criteria test because it's not covered in today's lecture, unfortunately, which is another way of checking the number of lags. But let's see if I can look at this model in first difference. Okay, I haven't created my first difference, so let me just make sure I'm getting this. Okay, so suppose I want to know what is the number of lags I need in my model. And remember, we're working with inflation in first difference. All I need to do is look at the very last coefficient, insignificant. Then my model is not AR4. Drop the last one and estimate. Just notice that I'm not going to talk about this one because I haven't covered it, so it's outside your materials. Now, AR3, it's actually 2. So I'm gonna stop here and say my model is an AR3, okay? And that's it. So your model is an AR3, okay? And now I have to change actually this. So AR3, because I was using the AIC. Now, suppose I want to expand this model and make ADL. So this is my model now, and the best model based on sequential hypothesis is AR3. Now, suppose that I want to expand this model and add lags of unemployment. So let's generate the lags of unemployment. Again, everything is in first difference, okay? And I'm going to use big to small. So I need 4 lags, okay? So let me just add it to the model I have here, because I have already decided that I have an AR3. I'm changing the do because I was depending on AIC, BIC. Now I'm using sequential, so I'm just going to make sure that, so this is going to be, I want to keep the AR3 so that you know. Okay, so let me say, okay, this is the AR3, okay? And now let's check ADL. I have already 3, so I know this already. Now what about the Q? So I need to do a block test for the Q, okay? And I need to check the 4 lags of unemployment. So this is how you do it. You perform sequential on the lags of inflation. Now you want to do the test PARM or the F-Statistic. And based on the F-Statistic, it's basically saying there is a 0 probability that these are equal to 0. In other words, my best model now, so I'm going to update this, the best model is ADL3, 4. That's it, okay? So I'm not going to, this is based on test, and this is block test. So this is the update, okay? So the best model now is ADL3, 4, and that's it. Okay, so I'm going just to remove everything related to information criteria so that you're not confused. And I wish I had the time to cover this, but we don't. All right, so I'm gonna stop here. And as I said, then tomorrow's recitation, I'll make sure to update the recitation so that it doesn't have information criteria and it's just covering whatever we were able to cover in today's class. In terms of the final exam, so the